start. Okay, cool. Recap workshop. So, Ashia has given you 4 weeks of content to actually prepare for the finals. Stiffness method for frames and beams. So I'm going to go through a question from your study pack for that, which does not have solutions. I hope you didn't finish it, but I'll finish it with you guys. Then force flexibility for trusses. I don't think this one has solutions as well, so I'll go through that. So this question I'll go through. Force flex method for frames and beams as well, so I'll go through a question for this. What was that? And one more question is the moment distribution method. So I have not done solutions for this. I'll figure it out. Sorry. Okay, I'm going to get started with the easiest topic. So easiest topic, I'd say force flexibility for trusses. Then it moves on to second hardest would be force flexibility for frames and beams. Then I'd say moment distribution and then stiffness method would be the hardest one. Mainly because of the matrix. Alright. Alright, cool. So I'll get started with this question here. So what I've done is I've broken down the steps that you guys are gonna have. So these are straight from my workshop, so I'm gonna go through them pretty quickly. All the notes I've got in my drive as well, which I'll send to you guys. So, first thing you're going to have to do is check your redundancy or your degree of indeterminacy. Right? The way you do that is using this one equation. Right? So, you can either, in this course, you can only have either a one-fold or a two-fold indeterminate. Anything above we don't look at for this course. So, one-fold or two-fold. Right? So, a few notes. If it's equal to 0, you have a determinant beam, which you'll be working with mainly for stiffness method. If it's greater than 0, indeterminate. If it's less than 0, unstable, which we don't work with, right? Then you're going to split into your primary and your redundant structures, right? If it's a one-fold, you only have one redundant structure and one primary. If it's a two-fold, you have one primary and two redundants. Okay, so one redundant for each degree of indeterminacy. And I'll explain how to actually figure that out. Next, you're going to have to solve your axial forces for the truss for each structure. So you're going to solve it for your primary structure and your redundant structures. Cool. And finally, to actually find your axial forces, you're going to need the help of your a table. So for your one-fold indeterminate, the table is quite easy. All right, it's quite small as well, pretty simple. For a two-fold indeterminate, it gets a bit longer. Okay, so I'm going to go through the two-fold really quickly because the question is a one-fold indeterminate, so I'm going to explain it anyways. But for your two-fold indeterminate, firstly you have your axial forces for each structure, so your primary and your two redundants. F, that's regarding your stiffness of the beam, right? And then you're going to have these 5. So the way I like to think about it is that you have F in all of them, and then you're just going to do a combination. So you have N0, N1, right? That's the first combination you can do. And you have N0, F, N2, that's the second combination. You don't do N0, N0, we don't look at the primary structure twice, we're only analyzing the primary structure along with one of the redundants. Then, what you have is, if I'm analyzing the redundant structure repeatedly, right, so N1, N2. N1 stands for the axial forces for your first redundant, N2 stands for your second redundant. And then you're going to have like a combination, N1F, N2, right? Which is equal to N2F, N1. So you're going to figure out these values for each member. And what you're going to have to do is you're going to have to sum them up and sub it into this equation here. And then use a bit of simultaneous equations to find x1 and x2. And to find the axial force for each member, you're going to have to use that formula there. Any questions about this? Nah. Cool. So, this question here, I'm pretty sure this one doesn't have solutions. Correct? Is that right? This one doesn't have a solution? Question 4. Yeah, okay, beautiful. So I'll go through this one. For the truss below, what is the maximum force P that can be applied before the member AE exceeds 10 kilonewtons? So this is a bit of a different question. They're not exactly telling you to find the axial forces, but you're going to have to do it anyways. Alright? So you're gonna have to somehow find the axial force of your member AE in terms of P. That's what we're looking at. Alright. Try to find axial force of AE in terms of P. First thing, what is my redundancy? So this is step number 1. Find my redundancy. When I sub into the equation, so number of members, I've got 1, 2, 3, 4, 5. So I've got 5 members. Number of reactions is your number of reactions. Yeah. So because these are pinned, each of them have 2. So 1, 2, 3, 4, 5, 6, 7, 8. Right. So I've got 8 reactions, and the number of joints, these ones also count as joints. So 1, 2, 3, 4, 5, 6. 6 joints. Sub into your equation, you end up getting a 1/4 into some B structure. Questions? No. Alright, cool. Now, because it's a one-fold indeterminate, I'm going to have to release a member. So in the case of trusses, what we do is we release members. Alternatively, you can release a reaction or degree of freedom as well. But that's more so for frames and beams. So I'm going to remove a member. Any idea? So I've released member 5, okay? However, that's because it makes it easier for me. In this case, you can release any member you want. Yeah. So if I were to, let's say, release member number 1, it would have the same effect as releasing member number 2. Oh, sorry, member number 5. But the main reason I release number 5 is when I'm drawing like at joint F. How many unknowns do I have? I've got 1, 2 unknowns in the x direction. So I can't really figure it out. Yeah, it's going to be pretty hard to figure it out. And then I've got another unknown in the y direction. Yeah. So I release this one to make it easier for me to find these unknowns here. Okay? Cool. So just have a bit of a play around with the structure. See which one makes it easier for you guys to actually release. So releasing member number 5, this is my primary structure now. What I've done is straight away I found the axial forces. So N3, oh my goodness, I've gotten this wrong. This should be P, this should be 0. Wow. Okay, I gotta change my whole working out. But anyways, I'm pretty much analyzing joint F here. So if I take a look at joint F, I've got N4 and I've got N3. So axial forces in member number 3 and member number 4, and this is my load P. In the x direction, we've got N3 is equal to P. In the y direction, there's no forces, so it's just going to be equal to 0. And I've said that it's in tension N3. And a trick for actually finding your axial forces, assume everything's in tension. If you get a negative number, that means it's in compression. Yeah? So down here, if I now analyze the joint E, this one here, I've got N1, N2, and I've got P, which is from N3. Okay, so this is from N3. Just do a bit of sum of forces in the x and y direction. So up here, I've done sum of forces with x. Down here, I've done sum of forces with y. Any questions? I'll give you guys a minute to copy it down. And I've gone N2 is equal to minus 0.75p, and N1 is 1.25p. You guys can take photos as well, that's alright. Alright, now secondary. So, first step for the secondary is to pretty much copy your primary, right? Then, second thing you're gonna have to do is release all the loading. So any external forces that are applied, get rid of it. So when I'm drawing my secondary, this is what I start off with, right? Because I've released my P, the loading, external loading, and then the member that I've released, yeah, I'm going to replace that member with a 1 kilonewton force. Any questions? Yeah, this is some simple stuff. And then I've got to figure out the axial forces for this one, which is lowercase n. Okay, well, I've got to fix up something in my table. N is equal to P. So these two swap around. So this should be 0. And this should be bar. This should be wrong as well. 1, 0. This one. Okay, so now I want to plug everything into my table. So this is just looking at joint F, joint E, doing a bit of sum of forces in the Y and X direction. I've kind of skipped those steps, but feel free to write it yourselves. If you're really good at doing your axial forces, you can just skip steps like I have, right? But you don't have to. Anyone need me to explain any of this? Alright, cool. So now, plugging everything into my table. So a key thing to note is for my F, it's going to be in millimeters. That's the units for it. So it's going to be millimeters per kilonewton. Alright. My N0 is just my primary structure, N is just my redundant structure. Sub everything in, find the values for these two for each member. 1, 2, 3, 4, 5, 6. How the hell are the 6 members? It should be down here. It should go up. This. Yeah, a bit more neat. There it is. Okay. So when I sum these up now, I get what number is that? 10,800p over EA. And for my second one, I get 14,080 over EA. So what you'll notice is that for this one over here, there's no P involved, right? So I get 10,800 divided by 14,080. Yeah. So I get minus 0.767 P. So I'm gonna color code this stuff. This is yes. This is this. Any confusion? That's to find my value of x. And now to find the axial force for your member, the formula itself is going to be n0 plus x times n. So n0 is just everything. It's already in the table. So because I'm trying to find it for AE, which I've defined to be member number 1, yeah. I'm gonna take a look at member number 1. N0 is 1.25p. N is just 1, so it's just gonna be. Why have I made it a plus? Should be a minus. Should be a minus here. This is wrong. When I sub it in, yep, I get 1.25 minus 0.753, 0.497p. So that's your member axial force in terms of P. And what we're gonna have to do is let this be equal to 10, because they said what's the maximum value of P before it exceeds it. Alright, so our maximum force is 10. So P, when I sub it in, so pretty much what they're looking for is that NAE has to be less than or equal to 10. 0.497p has to be less than or equal to 10. The maximum value for P is 10 divided by answer, you get 20.12. Why are you laughing? Are you paying attention? Sorry. Okay. Beautiful. Thank you. Any questions about this one? Nah. It's pretty easy. So this is why I said this is like one of the easiest topics. Yeah. Your study pack. So some of these don't have solutions. So this one didn't have a solution, so I decided to go through it. Yeah? Did you get a different answer? It's not question 4? Yeah, I think there's a bit of scrolling to do. Oh, good? Alright. Lovely. Alright, hold on. Shh. Hey. Shut up. Alright, next thing we're going to look at. If there's no questions, I'm going to move on to frames and beams, force and flexibility. You just said that. Alright, cool. So your first step is the same. Find your redundancy or your degree of indeterminacy. However, the formula is a bit different. So you have 3m plus r minus 3j. Is it still recording? Yep. 3m plus r minus 3j. So your members, your reactions, and your joints. Same shit. Alright? Second step is also the same. Alright? Pretty much all the steps are the same as earlier. Alright, except for the last few. So, you can either be a 1-fold indeterminate or 2-fold indeterminate. What I've also done, I've pretty much copied this from my tutor, Sharon, but these are your steps to help you draw your redundant structures and your primary structure and your redundant structures for a 2-fold indeterminate. So again, you're going to have to release one of the reactions, or you can also add a hinge. Right? Adding a hinge kind of like fixes up your indeterminacy, makes it determinate. For your redundant structure, you're going to get rid of the loading. Very, very important, because if you try to do it with the loading, it becomes hella cooked. Yeah? Now you can do two things. You can either add 1 kilonewtons at the released reaction. So if you release the reaction at the pin support, for example, so if you have a pin support and you've released one of the reactions, let's say you've released your horizontal reaction and made it into a roller, yeah? For your redundant structure, you're going to have to make sure you add that 1 kilonewton back. Yeah? Alright, cool. Alright, I'll explain this with the question. Actually, for 2-fold indeterminate, you can release 2 reactions, you can add 2 hinges, or you can do a combination. You can add 1 reaction, you can release 1 reaction and add 1 hinge. Up to you. I usually like to release 2 reactions always. It's just something I find a bit more comfortable. You might be a bit different. And then yeah, these are the steps from. Okay, now, in my steps, I've wrote that you have to find the B and D for your primary and your redundant structures. You gotta find your bending moment diagram if you're using the graphical method. Yeah? So your graphical method being, so this goes back to virtual work. You're gonna have to use this formula, AY over EI. If you choose to find the actual equations in terms of X, then this becomes, you're gonna have to do a bit of integration. I find that the integration way takes a lot longer compared to the graphical method. The graphical method, you might make a solution a lot more easier, right? So it's like a bit of a gamble. I'll try my best to simplify this method, and also sometimes you can't even use this method as well. It's a bit harder. Yeah, like for some of the study pack solutions, you actually can't use it because your load becomes triangular. Well, you can use it, but you're gonna have to like sort of bullshit it, I guess. So if your load's triangular, then your BMD is gonna be a cubic. Alright, so it's going to look something like this. And in your lectures, you don't actually have the area of the cubic in your lectures. Alright? If you try to use a parabola one, it's going to be wrong. So in that case, I'll probably recommend using the integration one. Okay? But usually, if they give you a primary, if they give you a triangular load, right, it's not too bad. to actually find the integration and do all the steps, blah, blah, blah. Okay.
Yeah, I have a question.
Yeah.
Can you like demonstrate how to do by integration? Because I always had trouble finding like the equations.
Okay, yeah. I'll do it from one of my workshops. Workshop examples.
Oh, you did already? Okay.
No, but I'll go through it again.
Okay.
Yeah. Okay, now finding your deflection. So this is the second step. So as I already said, you can use the graphical method or the integration way. Up to you. This same thing as virtual work method. So use the principle of virtual work method for force and flexibility. Yeah. What I'll do, I'll explain these subscripts. So you have 0, 1, 1, 1, 0, 2. Let me just explain these three real quick. So what this means, the 0 stands for the primary structure, the 1 stands for your first redundant structure. So you're pretty much finding the deflection. If you remember from virtual work method, you're going to need your primary structure and a redundant structure. Right? You're going to need both BMDs to actually analyze the deflection, the total deflection. So what you're doing here is you're analyzing the primary structure and the redundant 1 structure, and you're finding the deflection just for those two. Right? For this one, 1, 1, that just means you're using the redundant structure twice to analyze it. Right? So you've got to find a moment equation for your redundant structure, and you're going to have to like square it essentially. 0, 2 is just you're analyzing your primary structure and your second redundant structure. Okay? 1, 2 means you're going to be doing your first redundant structure and your second redundant structure, which is actually in fact equal to 2, 1 as well. Okay? It's just identity. So I'll explain this better with an example. Then you're going to have to find x. So 1-fold indeterminate is pretty easy. 2-fold indeterminate, again, you're going to have to do simultaneous equations. Okay, now, these are just some of the formulas you're going to need to find your bending moment diagram, shear force diagram, and axial force diagram. Okay. I've never seen a question for axial force diagram. I have seen shear force and bending moments. Alright, any questions? I'll go through an example then. This is the question. You guys don't have solutions to this, right? Or you guys do? I think you guys do. Yeah, no, not yet. No? I remember last year they gave us a study pack, but never gave us solutions for them. No? Okay, cool. Okay, I'll go through this question then. Alright, everyone paying attention? Alright, after this question, we're gonna give you a bit of a break. Why are you laughing? Lock in. So, redundancy. So first step again, find your degree of indeterminacy. Pretty easy. I end up finding it to be a 1-fold. Okay? Should I change the question actually to make it a 2-fold? No, I'll keep it as 1-fold. Okay? I'll show you guys the integration way with a 2-fold indeterminate. But cool. My primary structures, here it is. So what I've done is I've decided to release a reaction over here. Okay? So I've decided to release, over here usually there's a CY, there's a vertical, CX, and there's also a moment. Okay? When I try to graph the BMD, or try to find the values, we figure out that MC becomes a bit of a hassle. I like to always remove that moment first. This is just a personal preference. Doing that, I know that the value of the bending moment over here is going to be 0, over here it's going to be 0. Because at a pin support and a roller support, the value of the internal bending moment is always going to be 0. Okay, so I've released at C, and I've pretty much found the reaction forces now. So the reason I found the reaction forces is to find my BMD, shear force diagram, bending moment diagram. What's up? Question? Lock in. Pay attention. Alright, so I found CX, I found CY, AY, pretty simple. Alright, just a bit of week 1 content. Yeah. No? Anyone need me to explain it? Yes or no? Nick is saying yes. Makes sense? I appreciate that. So I found my shear force diagram over here, and corresponding to that, bending moment diagram. This one's a bit confusing because at this point you get a value of positive 18 for this number, but then over here you get a value of negative 18. And usually we know that at this point here, the moments should be the same, but why is one positive, why is one negative? Right? The reason is just the orientation of the frame. Alright, so if I, let's say, AB, AB, so I'm going to draw my B and AB like this. Let's say there's like another circle here. Then for BC, what I like to usually do is, because I'm cutting it from this side, I'm going to have to rotate it to make it into a beam. So essentially, BC. Yeah, it's a bit trippy doing it this way, but it works out. Or just trust your gut instinct. If you think you're doing the math correctly, you're doing it correctly. And I'll show you guys with this one website, Stryan. This is like one of my favorite websites for this course. Hold on. Stryan. And that's what the beam is. Why is it negative? Okay, if you just do the math, like this, like you tripped me out yesterday as well. It's like, why is one of them positive? Why is one of them negative? The actual reasoning behind it is like, it's like the orientation of the thing. Yeah, something like that. But honestly, when I was just doing the question, when I was doing the question, if you actually try to figure out the moment, the bending moment diagram for this one, I know that I've got a force here of 3 kilonewtons, and this is 6 meters. Oh shit! Sorry. This one. Yeah. The shear force diagram is obviously negative. Alright, so the bending moment is gonna be a negative value as well. I guess that's the only problem with getting rid of the moment. Your bending moment diagram for your primary structure might look a bit funky. Like at this point here? At this point here? Very good question. No clue. My understanding is it's just because of the orientation of that column. Does anyone have any better explanations? I'm sure it doesn't. Anyways, yeah. So it's going to be 3 times minus 3 times 6. So when I draw on the tension side, it's going to be on this side. Because I'll take this as my positive, this is my negative for the tension side. Alright, cool. So now moving on to my redundant one, same business, but my BMD is a lot easier. Yeah, this is what a BMD looks like. There's no shear force for this column, right? However, there is a moment, so I have to be careful of that moment. Yeah, it's just going to be a -1 because it's going the anti-clockwise direction. And as you guys should know, when you're graphing an anti-clockwise moment, on the bending moment diagram, it's going to be a negative. A clockwise moment is going to be taken as a positive. That's something I like. That's the way I like to remember it. So, okay, I've done some calculations here, but what I've got here is my primary. And over here I've got my redundant. Okay, so I'm going to show you guys how to do it the graphical way, because I can't be asked integrating. Okay, so the graphical way, if you guys refer back to some of the notes, AY over EI, and you're going to have to find A and Y and EI for each member. In this case, they've told us EI is constant, so it's not too big of a problem. But A and Y, a few things to note. A, you can get from either the linear or non-linear curve. So fortunately for both of these BMDs, they're both linear. Y, it's strictly only from the linear. Alright, Y, the actual value of Y, it's the value of the bending moment at the centroid of your primary. So let's say my centroid for this triangle here, where is it? 2/3 of the way from the minimum, so it's going to be somewhere here. Yeah. So if I want to take the value of the Y, I'm going to have to find that location. So this is 2/3 L, and I'm going to find this value Y. So that's the value of the centroid. No, value of the bending moment at the centroid of your primary structure. Yeah, it's a bit tricky, especially when parabolas get introduced. It's a bit tricky. If it's triangular load, you just can't use this. You have to integrate it. Alrighty, so let's take a look at what I've done here. So first of all, I've broken it down into 3 different shapes. I've broken it down into a triangle here, a rectangle here, and another triangle here. It's mainly because for a trapezium, the easiest way to actually figure out the centroid is by breaking it down. Yeah? And work with the shapes separately. Finding a trapezium of finding the centroid of a trapezium is like, I don't even know how to fucking do it, right? So just break it up. Alright. So I'm going to take Y from this graph, and I'm going to take area from this graph. So 0, 1 means I'm going to take the primary structure and then the redundant structure as well. So for this shape over here, let's say shape 1, this is the area of 1. So it's just half base times height. And then I'm going to multiply by Y. So this is Y. The reason it's 1/3 instead of 2/3 in this case is because we're actually taking a look at the whole member. We're taking a look at the whole member. We're not just taking a look at this small member here. Alright? Well, you can do it that way, except when you're doing similar triangles, you're not going to be using 1 as your height. You're going to be using 0.5 here. Okay? So let's say, actually, I'll just show it to you guys. So let's say we've got 4 meters, because this length is 4 meters. Then I've got a height over here of 0.5 meters at the middle. No, 0.5 as my bending moment. And what I want to find is this value Y at the centroid. So this is going to be 2/3 times 4. Questions? Queries? So if I want to find Y using similar triangles, I do Y on 2/3 times 4 is equal to 0.5 all over 4. So the 4's cancel out, and you're left with Y is equal to 0.5 times 2/3, which is 1/3. feel like a lot of people are confused right now. Who's confused? Hands up. Don't be shy. It's alright. Yeah? Okay, I'll explain it again. So first of all, y is the value of this bending moment, the value of the bending moment from this structure. However, we're going to take the centroid from this structure. Yeah? No, I'm going to take the centroid of this triangle. Yeah? So the centroid of this triangle occurs somewhere here, right? 2/3 of the way. So let's say it occurs here. 2/3 times 4 meters. Yeah? So what I want to find is the value of this y. Y value. Okay, so forget what I was explaining before with the 0.5, but let's try to find the value of that centroid. Let's find the value of that bending moment, y. So I'm going to use similar triangles for this. I get 1. What's the length of this whole thing? What's the length? What's the length? 8. Good. It's going to be 8. And I know that the centroid is somewhere here. 2/3 times 4. Okay? And this is the value of y. So let's try to find the value of y. Y all over 2 on 3 times 4. Wait, does everyone understand how similar triangles work? Or do I have to explain that as well? Okay, I'm going to take that as a yes. Is equal to 1 on 8. So the height divided by the length. Height divided by the length. The ratio should be the same. So when I rearrange for y, I end up getting 1 on 3. Yeah? The other way to kind of understand, I'll explain it later as well. But you're just going to repeat that for each shape as well. So for your rectangle, the centroid acts halfway between here, so 2 meters from this point. So it's going to be 6 meters from this side. Because this from here to here is 4 meters, this is 2 meters. So I'm going to take 6 meters here and find this y value, which you end up getting to be 3 and 4. Just a bit of ratios, right? And then 2 on 3 you get for this small triangle here. Yeah. And then divide that by EI. And then I also did the same thing for this shape here. In this case, you don't even have to find the centroid, because no matter which value you take, your bending moment is going to stay constant at 1 or minus 1. Yep. And by the way, I've changed this as a plus because this bending moment is negative, this bending moment is negative, negative times negative, you get what? Positive. Alright? So when you do all of that, your deflection to be 138 on EI. Kind of make sense? What's that? Make sense? Yeah. I can explain this stuff later as well if you guys need. But the other way I was thinking about it, so this is what bending moment looks like. I've got a point, so the centroid is here. Then if I break this up, I've got a centroid here, and I've also got a centroid here. Between here and here it's 2/3, then between here and here it's 1/3, here and here it's going to be 1/3, alright? So pretty much this thing over here is going to be 2/3 of the whole length, blah blah blah, and then if this is halfway between that 4, I think I sucked that explanation. Don't even worry about what I was saying.
Essentially, you're finding the values of the bending moment on the secondary structure at the central of your final.
Yes, exactly. Yeah. So the value of the secondary at the centroid of the primary. Chris, make sense?
Yeah.
For sure? Yeah. Alright, cool. So now I'm going to look at my secondary twice. Okay? So this one's a bit easier because we've only got one shape here and another shape here. Alright? So where's the centroid of my triangle? 2/3 again. So somewhere here. So it's going to be 1 times 8 times 2/3 times a half. Let me bring the 2/3 to the other side. So this is my area. This is my y value. And this is just my area times my y value. So y is just going to be equal to 1 because my bending moment is just equal to 1. Alright, you're going to be 8.67 over EI. And when you sub that into your x equation, you get 15.92 kilometers, which when I sub it into here, I get 15.9. Yeah, so that's the value of my bending moment. So here it is. Oh my goodness, I forgot to draw this, but I'll figure it out. So first of all, I want to find my reactions. So this is the reaction on my primary plus x times my reaction at the secondary, which you get to be 4.76, which matches 4.76. Then cy, this is my primary. I get 4.24, which also matches. Then Cx is pretty easy because we know that for my secondary structure, Cx is equal to 0. So it's just going to be the same as my primary. And MC, so the value of the moment over here, which I released at the initial for my primary, that's just going to be the value of x, which is 15.92 kilometers. Okay? And this is going in which direction? I said it's going in this direction, anti-clockwise. So when I want to draw my BMD, did I ask for the SFD? Yes, I'm going to draw the BMD only. I'm going to start from this point over here. So they've taught us 15.92 kilometers. So on the tension side, it's going to be a positive. So it's actually negative, but flipping out, I get positive. It's going to be out here. Oh no, sorry, it's the other side. 15.92. And it's going to drop linearly until a value over here, like that. I don't know what that value is actually. It should be 2.08. And then over here, my BMD is going to start off at 0. It's going to increase. That I don't know. Is this reversed? This is reversed. Yeah, okay, cool. So the reverse just means that it's in the tension side. Yeah. So it's gonna look like this. It's gonna go down here. 2.08. So we get a positive, positive. Yeah, sorry. So this part should be a negative over here. This part should be a positive. Wait a second. Oh, I've got this value wrong. Sorry. This should be in the opposite direction. Sorry, that's why. So this should be a positive, this should be a negative. So it would be negative. Because, okay, I skipped a step for MC. We know that MC is going to be MC0. So the value of the MC in our primary plus x times MC in our secondary. Yeah, so here it is. And we know for our primary it's going to be equal to 0. And we know that x is going to be equal to minus 15.92. And this is just equal to 1. So your MC, you end up getting minus 15.92. Yeah? Because we initially defined it to be anti-clockwise, it's going to become clockwise. Because of the negative. That's why when I graph it here, it becomes a positive. Because clockwise on the bending moment, yeah, it's positive. Yeah? Okay. Do you guys want a break? Real quick? Which this is yes. Anyone want a break? Nick says break. Karis, you want a break? Yeah. Alright, I'll give you guys a 5 to 10 minute break. Then we'll continue with stiffness method. Up here. What did you say? Alright, that's alright. I'll give you guys a bit of a break. If you have any questions, come to the front as well. I can answer them. Yeah.
Good question. This one. Workshop question. It's clearly twofold answer, because 6 numbers, 0 reactions, 4 drives. Then they only make one redundant structure. Like why?
Wait, what? One structure, redundant structure.
Yeah, so yeah, and even the table they only do one, like lowercase n.
Oh. Wait. This is trusses. So M. That's 2 redundant.
Yeah.
Okay, did they say anything in the question? Turn the force. Pin connected truss. So I guess we have 3 numbers. Oh, I think it might be because of symmetry. Because you can. So don't you know how it's like if you have this number of equations and this number of unknowns, that's your redundancy? Right? Because it's symmetrical. Especially your forces as well, they're symmetrical as well. And you pretty much get rid of one of those equations.
Oh, so when you get rid of one number, you're getting rid of like 2 equations.
Exactly,
Oh.
yeah. The symmetry thing is a bit odd. Yeah. So yeah, be careful. Yeah.
Oh, this thing is to be load here up,
Yeah.
like instead of this.
Yeah.
How to solve that?
It's the same way. It's just like you just assume everything's about upwards and stuff. So imagine how you can have a force like going down like this.
Yeah.
You can also have a force going upwards like this. So,
But is it because the formula only like giving us the downward?
but are you talking about like
Yeah, the moment one. Yeah.
the free end moments, fixed end moments. Sorry. So the only thing with this one is if it's going upwards like that, it just means that your moments are going to be flipped, and then it's going to be distributed like this instead.
Oh.
Instead of going downwards like this, and like your moments going like this, it's going to be flipped.
Oh, the action trick.
Yeah, that's what I'm thinking.
For this one, I think the answer is
Oh, sorry?
yeah. So I was wrong here. How can it be? This one must be more than the complex one, right?
Is this going to?
Yeah. Because he found that 9,000.
I don't think we did this question actually.
Wait, is this the one we did just then?
Sorry?
Is this the one he did in the section before?
Yeah. For the phases. Logically, this one must be more than
Yeah,
this
I
one.
know what you mean.
Yeah.
Because this is
Yeah.
before you get to
Before,
compacted.
yeah.
Might have been a mistake.
Yeah, but they also add, it only gets compacted a certain amount, and they also add water to it.
When the water should reflect something. Total boiling. I'm not too sure about phase relationships. I'm not too strong with it. Must be this from the borrow area. So you're borrowing some soil. And borrowing from the I'm not too sure on that, sorry. He's outside if you want to ask. He's like somewhere here. I'll ask him if you want.
Is it you upload all of them
Yeah, they'll be uploaded.
on the drive?
Yeah, on the drive. I'll send you guys the drive as well.
I was looking at something,
Yeah.
and I saw in this question, right, where when we draw S1 and S2,
Yeah.
and like here at this like roller support, I think they said neglect axial, that's why. So at the moment, you see, like they're kind of reversed, right?
Yeah.
So would you kind of like I was thinking, is that maybe why when you have like a 90-degree on like a frame? Because you're talking about like putting them out like this, right?
Yeah.
And when you do like that, the moment at that point has to switch.
Has to switch, yeah.
Right? So do you think that's why it becomes a negative? Because you're kind of like if
It could be, like at that point to counteract it.
yeah.
That could be a reason. But usually, because like when you looked at the other stuff, let's take, is it? Four maybe? 45 maybe? No.
You're looking for frames?
Yeah, I think it was
Frames is
one.
7.
Must have been week 1. Like, is there a frame question I want to read? Like over here, for example, like the bending moment at this point from this member and this member must be the same. That's not always the case.
Like it shouldn't be negatives of each
Yeah, like
other?
you see how there should be negatives.
Yeah.
It's a bit of an odd one. But I think you might be right.
That's just really confusing. Why does it not?
This is positive, this is negative. Oh, I think you are right. Because this is negative. Tension side. I'm gonna have to check. I think my understanding is a bit off. I'll check after. I'll have a sauce of it. But I think it just might be the orientation because we're cutting from the right, left. It's a bit of a different orientation.
Right. Yeah, well, I guess it would be the same because like,
It's counteracting.
like when we, just like when you cut it and you take it from the side, you flip it and you.
Yeah.
It's just confusing.
Yeah, this is confusing. Fuck. I'll take a look. Before that. Alrighty, let's get started. Okay, stiffness method. This one doesn't have solutions either. Alright, listen in. So, for the steps in general, exactly the same. So you got to label your structure, helps a lot. You got to create your location vector for each member. Find your local stiffness matrix for each member, which is a bit tough, right? It's a bit odd. And just a note, If they ever ask for internal forces or draw your bending moment diagram, anything like that, don't cross out the zeros on 0 rows. Just cross out the columns, you'll be fine, not the rows. Next, make your global stiffness matrix, so I'll go through how to do that. Creating your load vector is a bit tough. There's 2 scenarios, so if you have a scenario with your load being within the member, you're going to have to use your end moments using this diagram, which they actually give to you. Okay. Then
Sorry, that's if you have a
load within the member.
load within them.
Yeah. Okay. Cantilever or fixed? Make it fixed. Yeah.
Yeah, so how come some of them have a roller?
Those are just different cases. So if your end one is like a roller, then you use the roller one.
Oh, you wouldn't have to fix it.
No. It's only for the internal one that you cut. Yeah. Then finding your node of displacements. This requires you to actually inverse your matrix. My way of doing it is just using simultaneous equations. It's a bit easier. If you don't, because I don't know how to flip a matrix, so finding your internal forces, I'll go through how to find that as well. And here are some special cases which you guys can read after, okay? Are you going to office? I might go with it. Oh, okay, it's fine. Alright, get up. Fuck off. Okay, so this is the question I'm going to go through. Alright. So for the frame shown, find the support reaction using the stiffness method. What is the maximum internal bending moment for each member? So you're going to find the bending moment diagram for each of them and find the maximum. So I've labeled my structure. So I've labeled the direction. So this one's going this way, this one's going this way. Let me actually make it a bit more evident. And this one is going this way. Next, my degrees of freedom. I've also labeled this to be member 1, member 2. So member 1, member 2. And now my degrees of freedom. So at a fixed support, it's going to be no degrees of freedom. Right, it's restricted fully. At a joint, you're going to have 3 degrees of freedom. Again, at a fixed, none. One thing I want to really actually go through, which tripped up a lot of people last year, right, is the way that Daniel Oshie actually presents you the question. So last year, so let me move this out the way, he actually defined the degrees of freedom for you. So he said 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 degrees of freedom. But the way that Daniel explains it is that there's going to be closed degrees of freedom and there's going to be open degrees of freedom. Closed degrees of freedom is going to be 1, 2, and 3. So there's no degree of freedom there. 7, 8, 9. And these are going to be your only open degrees of freedom. So pretty much when you're making your location vectors, if you have like 1, 2, 3, 4, 5, 6, you know that 1, 2, 3 are going to be closed. So it's going to be equivalent of making them equal to 0. But I just like to make them 1, 2, 3. You can even do 1, 2, 3 in your exam. You just got to tell them, just write down and be like, oh yeah, these are my open degrees of freedom. Fuck you guys pretty much. Alright, what they present. Okay. So for member number 1, which is this one here, my lambda x is 1, lambda y is 0, and my length is 5,000 millimeters. So I put in millimeters is because everything up here is in millimeters, and when I convert my units for GPA, it's kilonewtons per millimeter squared. So I'm going to keep in millimeters. Cool. So I can cross out the first 3 rows because it's just 0. So first 3 columns. And I noticed that lambda y is 0. So there's a lot of things I can cancel out. So lambda y is 0 here. This is going to be 0. This is going to be 0, 0, 0, and 0. This just makes my life a lot easier, okay, when I'm actually subbing in. This is 0, and all the green ones are the only ones that I have to find. So when I subbed it in, I've got my location vectors, and this is my local stiffness matrix, after you plug it in. Is anyone copying it down? Bora, are you copying it down? No? No? Okay. So if no one's copying it down, I'm just gonna go over it. Number 2, my lambda x, so here it is. So it's at like a 45-degree angle, yeah? So because we know lambda x is gonna be cos theta, it's just gonna be 1/√2. Where theta is gonna be equal to 45 degrees. And this, in fact, is equal to lambda y as well. Yeah? Oh, hold on a second. Lambda y is going to be a negative here. This should be a negative. Fuck. Because it's going downwards. Alright, okay, so I've actually messed up my local stiffness metric, so I'm going to fix it up live. So, that's fine. This becomes a negative. That's fine. This becomes a positive. And that becomes a positive. Number 2, this becomes a negative. This becomes a positive, positive. This becomes a positive. This stays the same, stay the same. Stay the same, stay the same. This becomes a negative. Stays the same, stays the same. This becomes a positive. Okay, so that's my fixed one. Okay? So local stiffness metric takes a bit of practice, but you guys can practice yourselves. Compare it with my answer. If you guys find out that I make a mistake, just let me know whenever.
Wait, so
Yeah.
when can you like delete the rows and
Okay. So rows you can only delete if they don't ask for like anything internal forces related. So your bending moment, your shear force diagram, if they ask you for that, you can't get rid of it.
Yeah.
Yeah? If they ask you just for displacement, like of your member or like a point, you can get rid of it.
Okay.
Yeah? Okay. So now my K global. How do I find my global stiffness matrix? So if I'm trying to find this square here or this point here, I'm gonna have to take a look at the intersection of my location vectors. So 1 and 1. So I have to go to both of these, take a look at where 1, 1 intersects. So 1, 1, that's horrible. 1, 1, so it's going to be 400 first of all. It'll be 400. And then I take a look at my second stiffness matrix. 1, 1, I get 177.08, and I'm going to add them together. And I end up getting 577.08. Questions? Does that make sense? Yeah? Now, a thing to notice is that it's actually symmetric. So for 2, 1 and for 1, 2, it's going to be the same value. 3, 1 and 1, 3, it's going to be the same value. 3, 2 and 2, 3 is going to be the same. It's just the only ones that aren't the same are going to be your diagonal ones. Okay, so for 2, 1, I get 2, 1, and then 2, 1 is 0. So it's just going to be minus 1767.47. Alright? And then for 3, 1, so 3, 1, 1193.24. So this becomes a positive. And if I go up here, 3, 1 is 0 again. So this becomes 1193.24. I'm going to take a look at 3, 2 real quick. So 3, 2, I get minus 2160 plus 3, 2, 1193.24. Which when I plug it in, 1193.24 minus 2160. I get minus 966.76. Wait. 3, 2, 3, 2, 2. Okay, I've made a mistake here. There should be a minus. Yeah. Okay, beautiful. And then finally 3, 3. This is an absurdly huge number for some reason. I don't know. 3, 3 plus 3, 3. So I just got to double that number. You get 12.73 times 10 to the 6. Okay. Now, next step is to find. So I've done my k global. So k global is done. Next step is to find my end moments. So scroll up a little. I'm gonna have to use this diagram for each member. Okay. So because I've got a load within the member, load within the member. So I'm gonna split it up. S1, so S2, wait, hold on. What was I gonna say? I forgot, okay. So, first of all, this is 3 meters. This is 2 meters. Same thing there. So I'm gonna have to use this formula here. Okay. Your S1, if I scroll up, your S1 represents like all your internal forces, right? Your S2, where is it? It represents the effect of the load acting on the member. So it's pretty much like an external force that's been distributed, right? To the endpoints. So I'll scroll down. So S1, I've got that going upwards, but then when I distribute it, you can see that this plus this equals to 30 kilonewtons. So it's like the effect of that load is distributed to the two endpoints. Yeah? And because it was just a joint, I just make it into a fixed support. Okay, member number 2, I've got this case, this scenario, where this is L2. So L2 is a bit weird. So the actual length of this member, because it's a diagonal, right? It's a diagonal. It's going to be in millimeters. It's going to be, or in meters, it's going to be 4 root 2 meters. Yeah. Any questions about how I got that? Yeah, just a bit of trig. Again, just flip it, and that's your S2. Yeah. I'm not going to really explain how to sub in numbers, right? You guys should be able to do that. Now my load vector. So load vector, because I've got 3 degrees of freedom, it's going to be a 3 by 1 vector. 3 by 1 vector. N equals 3 means that N is the number of degrees of freedom we have. Okay. So if I had like 6 or 7 degrees of freedom, right, then it would be like 6 rows for your vector, right? Wait, one sec. Okay, so 1 is the thing that's going in the horizontal direction. So as I defined it up here, 2 is our vertical direction, 3 is our moment. So moments, they're going to add up at the point. So this point and this point, they should add up. One's going anti-clockwise, one's going clockwise. So this value is actually very wrong. Let me fix up that value. 21.6 minus 27.5 minus 5.9. So I'm pretty much taking, because these two combine at this point, we're taking a look at the total sum of moments at that point, right? So 21.6 is going the anti-clockwise direction, which is positive. 27.5 is going the clockwise direction, which is negative. Alrighty. Then in the vertical direction, we've got these two adding up, which is going downwards, and then we've got no horizontal forces. Just be wary, I'm actually not too sure myself, because this is at an angle, the force might be going in this direction. Like that. Let me check. Let's try and save the day. It's going up by 4, to the right by 5. supports fixed. This one, this one. I see it's weird because they. Dirty. And then I've got a UDL 15. That's what I'm thinking. It's a bit tricky. That's like a flaw in the question. They haven't told us which way it's acting. They have, but okay, let me check. This angle. It's like it's acting at a 45-degree angle. 5. One sec. Okay, like this. Alright, that's better. That's better. Oh, maybe I should change the support as well. No, that's fine. That's looking very odd. I can't lie. We'll figure it out. Yeah, so let's just rock with this P for now. And what I'm going to do is I'm going to solve for U1, U2, U3 using simultaneous equations. So the first equation is going to be 0 is equal to 577.08 U1 plus 1767. Oh shit, sorry. I'm going to have to change all these numbers. So 577.08 U1 minus 1767.47 U2 plus 1193.24 U3. Equation 1. Then minus 53.91 is equal to minus 1767.47 U1 plus 981.08 U2 minus 966.76 U3. And lastly, 34.1, 1193.24. Sorry? Oh yeah, you're right. Minus 5.9. U1 minus 966.76 U2 plus 12.73 times 10 to the power 6 U3. Okay, so we've got 3 equations, 3 unknowns, so it is possible to solve. Just a bit tough. Let me try to figure this out. U1, take it that side. Okay. So what I'm going to do is I'm going to take equation 1 and I'm going to make U1 the subject. So I get 577.08 U1 is equal to 1767.47 U2 minus 1193.24 u3. What I'm going to do, oh wait, I forgot to make u1 the subject. u1 is equal to 1767.47 divided by 577.08. Okay, 3.063 u2 minus 1193.24. I get 2.068 u3. Okay, what I'm going to do with that is I'm going to sub in this value into this, my equation number 2 and 3. What will happen with that is I get two equations in terms of u2 and u3, and I'm going to first of all simultaneously equation those two, find u2, u3, sub back into my first equation to find u1. Okay, so let's say equation number 4 becomes minus 53.91 is equal to minus 1767.47 times 3.063 u2 minus 2.068 u3 plus 981.08 u2 minus 966.76 u3. Fuck now. 1767.47 answer plus 981.08. So I end up with 4635.714 71 u2 minus 3.063 times minus 1767.47 minus 6830.52 u3. So this is going to be equation number 4. Now I'm going to sub it now into this one, so minus 5.9. 1193.24 times 3.063 u2 minus 2.068 u3 minus 966.76 u2 plus 12.73 times 10 to the power 6 u3. I end up with 1193.24 times 3.063 answer plus 12.7. I end up with 12.73 times 10 to the power of 6 u3. Doesn't make much of a difference. Minus 1193.24 times 2.068 answer plus 6.76 3434.38 u2. So this is my equation number 5. So I'm going to solve equation number 4 and 5. You end up getting u2 is equal to something, u3 is equal to something. My fucking god, this is so much work. This is why I don't like this topic, but let me quickly figure it out. Hello, Simple Lab. You guys can do it yourselves, but I cannot be doing that. Minus what the fuck? Okay, anyways. So you find U2, U1. Fuck off. Okay, so you find U2, U3, then using these you find U1 as well. I think some of my numbers are cooked. Right? But then after you find those, right, you're gonna scroll up a little. After you find your node of displacement, so that gives you displacements at degree of freedom 1, 2, and 3. Yeah? But for your third one, it's gonna be a rotation. Alright, it's not gonna be a displacement. You're gonna find your internal forces using this equation. So your P over here is gonna be KI/UI. So KI stands for your local stiffness matrix. Yeah? So you're gonna sub in your local stiffness matrix and your local displacement vector as well. That's going to be a 6x1 vector. So if your location vector is going to be 0, 0, 0, 1, 2, 3, and these are just going to be 0, and then you sub in U1, U2, U3. If it was like 0, 0, 0, 1, 2, 4, something like that, 0, 0, 0, U1, U2, and then U4. Okay? So it has to correspond to the degree of freedom that you're looking at. Alright, and then you also got to add S1 to find your internal forces. Alright, pretty much after you do that, you get a BMD that should look like this. What's going on? I feel like this support is a bit cooked. Yeah. I think the reason Daniel didn't make solutions for it is because the question's a bit flawed. Like over here. Anyways, this is what it should look like. So after you get your fucking hell. That's what you've been using. Okay, a thing about this question is like, you might make a mistake over here, or you might make a silly mistake over here, right? As long as you show your understanding, right, you get most of the marks. If you make a small mistake, it's alright. So, like over here, if you make a mistake, like finding a displacement, or, yeah? Oh, fuck, sorry. Thank you. Yeah, so if you make like a mistake, like here, or like here, alright, not too big of a deal. You lose a few marks for sure, but if you show your understanding for the rest of the steps, you can even bullshit if you want to, alright, you get most of the marks. Okay, I don't have time to go through the rest of this question, but I might write up the solutions later on and then upload it. But now, I'm going to go through a moment distribution method. Okay? They didn't ask this question last year, so I don't know any info about it. About how Daniel might assess it. I do know how to do it, but like, I don't know how Daniel might assess it. Right? But these are the steps. So you're going to break down your beam into multiple segments. Yeah? So you've got AB, BC, and CD. If you have an external support, so for example, this would count as external support, this would count as external support, you keep it the same. You don't change the support. However, if it's an internal support, so like this one and this one, you're going to change that into a fixed support. Similar to what I was talking about the fixed end moments in that diagram, you're going to keep it the same. In fact, you're going to have to use that somewhere here, yeah. You're going to have to use this as well for the moment distribution. Second step is to find your flexural stiffness for each section. There's two cases. If you have fixed, or fixed pinned / roller. So if it's fixed, your flexural stiffness is going to be 4 EI on L. If it's fixed, pinned / roller, it's going to be 3 EI on L. Yeah? So for example, if I go up here, this is going to be 4 EI on L, 4 EI on L, 3 EI on L. Yeah? Then you're going to have to find the distribution factor for each node, DF. So a few of the easier ones is DF at a fixed support, like on your original beam, like this. So over here, for a fixed support, it's going to be 0. So that means the moment's not distributed, that support takes on the whole moment. At a pin support, or a roller support at the end, so something like this, your distribution factor is going to be 1. Yeah? But for any of your internal cases, so something like this, you're going to have to use this formula here. So it's going to be k divided by the sum of all the k's attached to that node. So for example, if I had something that looks like this, and I'm trying to find the distribution factor for this node over here, I'm going to have to take into account this node, this member, and this member at the bottom. Usually, they might ask you something like this, but if it's just 2, then you only have to care about this member and this member. So any of the members that's attached to that node here. So you see over here at node B, I've got member AB to worry about and member BC to worry about. Yeah?
Why do you
Oh yeah. So, KAB is equal to KBA.
Oh,
Yeah, it's just a fractional member of that member. But the only weird thing. Okay. Oh, like why don't you use BC? Gotcha. So it's just to do with the notation. So they're saying find a distribution factor of node B from the side of A. Yeah? So node B from this side. Yeah? Then this is going to be node B from C side. That's why up here I use BC, for this one I use AB. And in the case of, let's say at this node, all the distribution factors should add up to 1. Yeah. So in this case, because I've only got 2 nodes, the distribution factor from this side and this side is going to add up to 1. Okay, cool. Now fixed end moments for each section. So for each of these sections up here, you're going to have to find a fixed end moment. So this is going to be given to you. Alright, and this is just the example that I've written. So let's say this is 150 kilometers. This is 8 meters. This is 6 meters. And then these values are just straight from up here. You only have to find the moments, not the forces. Okay, so don't worry about finding the forces. We're just caring about the moments. Okay. Nelly, the second last step is to fill in this table. Okay, so you're gonna have to memorize this table. You're gonna have to find it for each. You're gonna have to find the values for distribution factor and your fixed end moments for each node. For each node, yeah. And a trick is to start from the middle. So you don't start from the end moments. You start always from the middle. Okay, what I've done over here is I've listed out some key points. So 1, 2, 3, 4, 5, and 6, and the formula for each point. Okay, so I'm gonna if I got to see in my exams, I'll probably refer to this. I'll be like, okay, for point 1, I'm gonna add up the fixed end moments, and I'm gonna multiply it by the distribution factor. From point number 2, I'm gonna add up the moments, multiply by the distribution factor. Okay, now when we're trying to distribute the actual moment up here, one thing I actually forgot to mention. If your distribution factor is equal to 0, you actually can't distribute the moment, so it stops. And if it's at 1, that means it can't receive a moment. Okay, so I'll show you what it means. So over here, imagine, so when I'm distributing that moment, it's always going to be times 0.5. It's always going to distribute half of the moment. It's just a rule. The actual theory behind it I forgot, but that's just a rule. So let's say that over here my degree of freedom, distribution factor is 0. So it receives the moment, however, it can't distribute it. So I'm not going to multiply by 0.5 again, I'm just going to stop that process here. So for this column here, I just stop the process of distributing the moment. Okay? Imagine this distribution factor was equal to 1. What would that mean? Yes, exactly. That means this over here cannot distribute that moment. So that means this wouldn't exist, and it would literally just stop right there. Yeah? Fine. Okay, so over here you're going to keep distributing, so 5, you're going to take these fixed end moments and add 4 as well, and do the same here. So add your moments, add 4, but the only thing that changes is your distribution factor, so you're going to have to be careful about that. So at the bottom here, you're going to have to sum up all the moments on each side of the column. Right? Over here, you're going to get like a minus MA, so that's going to represent your moment at A, but the negative direction. So to actually find your moment at A, you just multiply by -1. That's for sure it is. After you do that, you find all the reactions. So if you have the moments here, yeah, you're going to go back to your fixed end moments part. Right? You can actually figure out AY and BY over here using sum of moments. Okay? Now, just a thing to note, let's say you have multiple sections. So let's say one section here, another section here. So let's say you have A, B, B, C. Something like that. And over here, you're going to have some force here, some force here, some force here, some force here. Okay? So after you find the reaction, so you're going to find AY. However, you're going to find two BY values. So you're going to find the BY value for this member, you're going to find the BY value for this member. Those two, so this represents the shear from the left-hand side, this represents the shear from the right-hand side. If you want to find the total reaction, BY, you're just going to have to add them up. So this is what I mean by section 1, section 2. So if this is section 1, section 2, and imagine if there was a roller over there, like in reality, this BY value is just going to be the combination of what I've broken up. Questions? Leo, Jade, anyone? Questions? Nah? Alright, cool. And there's obviously a special case where you have a cantilever. So cantilever, pretty much what happens is you're going to have to convert this force into a moment and a singular force. So, like, if this distance is d over here, that means there would be technically a moment PD acting at that point. It causes a moment, right? Because this is your member cantilever. Yeah, like it's going to turn. That moment is just force times distance. So P times this distance here. So you're going to convert that into a moment, and you're going to move that force at that point. We don't really work with cantilevers. We just like to, you just end it off here, and it becomes like a fixed. It's a bit confusing, but this is a workshop question that covers it as well.
So it's just like that whole question you talk about, you have a cantilever side and then
No, you don't cut it up like this and then look at this member. You would you'd cut it off here. You'd ignore this part, but that's why you'd have to convert this into like an equivalent force and a moment here. Yeah. So you'd cut it up here and here, make it fixed, and there would be like that external moment acting there as well. It's a bit tricky, but this is the question I plan to go through, but we are running out of time. Does this one have solutions or no? It does? Okay, I guess I'll go through like a few steps. So first thing, you'd have to break up the segments. So this would become a fixed, this would become fixed. So your section AB would look like this. Then you'd also have this section BC. Then you'd have another section here, like this. Of 4 kilonewtons. The flexural stiffness, so K over here would be 4 EI on L. K over here would be 4 EI on L. You'd actually have to plug in the value to figure it out. 4 EI on L. The distribution factor, so DF at A of AB, what would it be equal to? What would the distribution factor of DF AB be? 0, 0, this is fixed. Alright, DFBA, in this case it actually wouldn't be 0, even though it's fixed here. What we care about is like the original structure, not the broken down one. So it would be KAB all over KAB plus KBC, which in fact just equals to 0.5. DFBC is also going to be equal to 0.5 because we know that these two have to add up to 1. Because at this single point, node B, this member and this member is like the thing. Similarly, DFCD is going to be 0.5 as well. And DFDC is going to be what? 0. 0, right? Because it's fixed. So pretty much we're saying that we're starting off at, we're looking at the node D, but on the side of C. Yeah?
DF, BC and CD should be 0.5 because the lengths are different, right?
They're the same.
Then it doesn't find it.
Oh, so this one.
BC and CD.
Oh, gotcha. Okay. So this one should be different. They said this is just EI. This is just EI. This one's going to be 0.8 EI. Okay, so this should be 0.5, but DFCD should be a bit different. It should be EI all over 1.8 EI, which you get to be 0.55. Oh, this is a bit tricky though. You said this is 0.5 BC. Yeah, that's at the node B. Oh, then you also have to find CB. Okay. DFCB. This should be just 1 minus, so you get 0.44. 4. Yeah? No? Okay, so no, BC would stay the same because we're looking at the node B. CD, we found it to be 0.556, but CB would be 0.444. And these two add up to 1.
So it's not the forces between, because the forces like on the joint.
No, this isn't the forces. This is just,
The distribution.
yeah, it's on the node. So we're looking at the joint A, B, C, D, not the whole member. Confusions? Nah. What's up? Makes sense, sort of? Alright, cool. So after you find degree of freedom, you just gotta, distribution factor, you found K, you gotta find your fixed end moments, so you gotta find this one, this one, this one, this one. So this one is PL on 8. This one is WL squared on 12. This one, I'm not too sure. It's like PA squared B over 12. PAB squared on 12. Something like that. Or 192. I don't know. But you can figure that out. And then you're going to draw your table out. So after you sub it in here. So pretty much these two have to add up to 1. These two have to add up to 1. These ones can be 0 or 1. Yeah? And then you just got to distribute the moments. Okay? The general note is that you're going to keep repeating this distribution step until this value of your moment becomes less than 0.1. So it might take like a few tries, a few repetitions, right? But that's like the main thing about this question. Everything else is pretty easy. Like I've pretty much done all of this, like half the question in, I don't know, you can probably do it in like 5 to 10 minutes, right? Maybe even less. And then this one you probably have to spend quite a bit of time doing it, maybe another 5 to 10 minutes. Yeah? Yeah. Oh, that's the thing I just explained. So this thing inside of the table, so you keep distributing it, until that value becomes less than 0.1. 0.1 or close to 0.1. It might be 0.01. Sorry. Oh no, just less than 0.1. Or just something in general.
Is it any open as soon as one becomes less than 0.1? Because in the solution itself, at the end of the number, let's get -6 and 8.8.
Oh really? Oh, like these solutions? Yeah, I'm saying like the solution that they have. Where did that end at?
Like at the very bottom, they have 4 at one place.
Yeah.
And they have 0.96, 0.011, and 8.8.
They end off at 0.0111. So it would be for each individual. So let's say for this column, I end up with like 0.09, something like that. I'd stop that column there. Then I'd keep continuing for this column until that goes less than 0.1. Yeah. So you keep continuing for like each column here, until it's less than 0.1. I don't have solutions prepared for it, but the solutions on the thing are quite good as well. Yeah. And then after you find your moments, you're gonna have to find the reactions at each point. That's gonna help you find your shear force diagram and then your bending moment diagram, and that's it. That's the question. So I couldn't go through like this part here, but we'll end it there. So I'll stop the recording now.